My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 559. In this lecture, I will continue my discussion on ReLUs. I request you to go through my previous lecture, that is lecture number 558, before understanding this lecture. Recall what is my ReLU function f of z equal to max of 0 comma z, which is equal to 0 if z less than or equal to 0, z otherwise. Geometrically you can say this is a ReLU function, isn't it? This portion is related to f of z equal to z as z is greater than 0. If z less than or equal to 0, what is this portion? Your f of z equal to 0. This we already discussed in our previous lecture. This is a derivative of f of z. Here just see, here what it indicates, derivative of f of z with respect to z. If I differentiate 0 with respect to z, 0. Of course, your derivative is not defined at equal to z equal to 0. That's why what we are doing, just we are saying we are defining you are defining if z less than 0. That's why I am removed equality symbol here, isn't it? Therefore, z with respect to z is 1. Therefore, d by dz of f of z is 1. What is this one? This is d by dz f of z means z greater than. Z greater than means this is 1. If z less than 0 means this is d by dz of f of z equal to 0 here. For z less than 0, your derivative is 0. For z greater than 0, your derivative is 1. This we already discussed in our previous lecture, isn't it? We need to understand why is this ReLU useful? Why did we come up with ReLU in first place? Because we have the problem of, what problem we had? We had the problem of vanishing gradient with the tan h or sigmoid activation functions. That's why ReLU, that's why we are using ReLU, isn't it? Now, here imagine in the whole neural networks, if let's say, let me recall our lecture number 545, where we discussed about f11, f12, f13, f21, f22, f31. Again, this is fully connected. Of course, I have I have a vector x. Let me say my vector x is input vector. Just see, this is vector x. The diagram that we saw, this diagram we saw in lecture number 545. So here your each activation, if you recall your chain rule, in our chain rule we had the vanishing gradient problem because you are multiplying lot of derivatives, isn't it? We were multiplying lot of derivatives, because derivative of L with respect to, just try to recall, derivative of L with respect to W11 had complex multiplications of derivatives. Just see, we had complex multiplication of derivatives. I request all of you to go through this particular lecture number 545. We had multiplication of derivatives, and each of these derivatives in case of sigmoid activation are in between 0 and 1. We discussed this when we discussed the vanishing gradient problem just in the lecture number 545. Your derivatives are gradients, but in the case of ReLU, what happens? Your derivatives are gradients, either 1 or 0 in the case of ReLU. No derivative is greater than 1, because the derivative of ReLU is either 0. The derivative of ReLU is either 0 or 1. It can have only two values, isn't it? It is either 0 or 1. That's what it says. Derivative of ReLU with respect to z belongs to set of 0 comma 1. Since it is always it takes either 0 or 1, you will not encounter much of exploding gradient problem, isn't it? You will not encounter much of exploding gradient, because the maximum value of gradient is 1, because you will not find values like 0.1, 0.2 or 0.3, and we are not multiplying these we are not multiplying these. You don't have even problem of vanishing. You don't have even problem of vanishing gradient, isn't it? Why? Because your derivatives is not in between 0 and 1, but because there is a value of 0 here, just try to understand. This takes value 0. You could have a problem called dead activations. I will explain you what dead activations are literally in a little while. But before that, let's understand why do we need this. There is a very nice paper by 3 persons from University of Toronto. Just these are the 3 authors. I really from this particular paper, I really like this diagram. Very interesting diagram. And unfortunately, this is not multi-layer perceptron. It's not MLP. This is a different type of neural network called convolution neural network, CNN. But don't worry about it. Similar behavior can be found even in multi-layer perceptron. We will learn CNNs in next chapters. The most important part here is on the x-axis is, just see, the x-axis I have epochs, and on y-axis is the error. Obviously, as the number of epochs increase, your error rate should come down, isn't it? There are 2 lines here, solid line here. Just see the solid line. What is indicate solid line here represent a model that is built using ReLU. There's this dashed line. What this dashed line represent using simple model built by using simple tan H function. What do you notice here? After 5 epochs, just see, after 5 epochs, if you observe carefully, after 5 epochs, just after 5 epochs, tan H activation, and this is the tan H activation. Just observe, if you observe carefully, what's happening. And this is your if you observe carefully, this dashed one is tan H activation model, and the solid line one is which one is a model by ReLU, isn't it? You have an error. You have an error of almost 0.4, where you have an error of 0.4 with the model by using tan H function, isn't it? For tan H, you have a training error of 0.4 for tan H, but for ReLU, the error is 0.26 probably, which means for same number of epochs, we have much lower training error using ReLU, because ReLU converges faster. What does it shows? It shows that for 5 epochs, ReLU is having significantly lower error rate than your tan H, which shows that ReLU is converging. I can say ReLU is converging towards the solution, isn't it? ReLU is converging towards the solution faster than your tan H function. And why is this happening? Because you don't have the problem of vanishing gradient. We saw here the vanishing gradient problem slows down convergence, because ReLU does not have this vanishing gradient problem, isn't it? ReLU does not have this vanishing gradient problem, because your gradient is always either 0 or 1. So you don't have the problem of vanishing gradient, and I can say you don't have the problem of exploding gradient also. Hence, we are able to converge faster than tan H activation unit or sigmoid activation unit. That's the reason, that's the core reason why ReLUs are become super powerful today, isn't it? There are many variations of ReLUs. Go to the Wikipedia page. We see some of the variations. I want to explain the Wikipedia page, very well written Wikipedia page. As of 2017, the most popular activation function for deep neural networks is ReLU. We saw the definition of what ReLU is. Instead of here what we are doing, instead of Z, they put X here, nothing else. there is something called smooth approximation to ReLU, isn't it? What is that smooth approximation to ReLU? This is how ReLU function looks like. Just see the ReLU function here. This one is ReLU function, isn't it? Anybody can understand this particular graph. Yes, this one is ReLU, isn't it? This one is what is this? This is soft plus, isn't it? This is soft plus curve, isn't the here which I can say the smooth approximation to ReLU. This is how ReLU function looks like. The blue line here which I am highlighting here is ReLU activation, but ReLU is, we said it is not differentiable at 0. So people said, is there an easy way? Is there a smoother approximation to the ReLU? Such function is called soft plus function. Soft plus function is interesting. Soft plus function definition looks like f of x equal to log of 1 plus e power x, and the function looks like this one. What is this? This function look like this soft plus function curve is like this, isn't it? And the function looks like this particular curve. This is like approximation. The soft plus is very close to your ReLU function, isn't it? ReLU very close to ReLU line at most places, ReLU curve at most places except at 0. That's okay. It's like a smooth approximation. So sometimes people do use soft plus function, and the derivative of soft plus function, if you observe, the derivative of soft plus function is the logistic function. Just see, this is my soft plus function. If you observe carefully, this is soft plus function. Just I am differentiating. Differentiation of log x is, what is differentiation of log x? 1 by x. Therefore 1 by 1 plus e power x. Again internal differentiation, 0 plus e power x. E power x is differentiation is e power x. E power x by 1 plus e power x. Just how can I write? E power x by, if I take e power x common here, 1 plus e power minus x, you will get here this and this will get cancelled. Ultimately what will you get? You will get your f dash of x. You will get, it will be 1 by 1 plus e power minus x, isn't it? That's the derivative of soft function is the logistic function. That's the fun part. That's the fun part here, isn't that? That's the fun part. The derivative of soft plus is logistic. People have used soft plus in some cases. That's not very popular. Actually ReLUs are more popular, isn't it? Computing derivatives of ReLUs is very simple. If you remember, what is the derivative of ReLU with respect to z? It is 0 if z less than 0, 1 if z greater than 0. What is the derivative of sigmoid unit or tan h function? This calculating derivative for sigmoid unit or tan h functions are far more complex if you compare with ReLU function, isn't it? What is my d by dz of tan h is 1 minus tan h square z. You have to compute some of the complex function like tan h z here. Even the derivative of sigmoid is basically, what is the derivative of sigmoid? Sigma z into 1 minus sigma z. So you have to compute the sigmoid function. What is the sigmoid function? Contains exponential. What is my sigmoid function? 1 by 1 plus e power minus z. Means in sigmoid function you have exponential function. Here we are computing the exponential function in the case of, but in the case of ReLU, in the case of tan h function, in the case of sigmoid function, we have exponential functions. But in the case of ReLU, computing the derivative is extremely simple. It's trivial. It's like if-else condition. Computing the derivative is literally like derivative of ReLU is like if-else condition. If z less than 0, output is 0. If z greater than 0, then output is 1. It is as simple as, which makes ReLU extremely fast, isn't it? Which makes your ReLU extremely fast as compared to your sigmoid or your tanh. In addition to not having vanishing gradient problem, it is also extremely fast, extremely simple to compute the derivative of ReLU. Having said that, let's look at some variations of ReLU. There is something called noisy ReLU. Yes, there is something. There is one variation that is called, of course it's extremely fast. That's what we were discussing. Calculating derivative of ReLU is extremely fast. Now there is something called, we now look at some variants of ReLU. There is something called noisy ReLU. Noisy ReLU is a simple idea. It says that the definition of ReLU is, what is definition of ReLU? F of x equal to max of 0 comma x. Here they want to make it slightly randomized, so just they are adding random variable here called capital Y. Just they are adding a random variable capital Y, which is sampled from Gaussian distribution with small variance, isn't it? Noisy ReLUs are used in a special models called randomized Boltzmann missions, very oftenly used in standard multilayer perceptrons. In multilayer perceptrons, very oftenly used in standard multilayer perceptrons. But just we will try to understand about this noisy ReLU in future classes. I request all of you to go through this particular lecture. In my next lecture, that is in lecture number 560 also, I will continue my discussion on ReLUs. Thank you very much.